Welcome to the first video lecture in the series of video lectures about lexical analysis, which is the first component of the compiler pipeline. The lexical analysis phase of the compiler is responsible for taking an input program, which as we know is a string, and convert it into a stream of tokens that will be then further used down the line by the rest of the compiler. So let's take a look at an example where I have this input string, which is like a fragment of a program. And the job of the lexical analysis to identify double as being one of the reserved words in the programming language, and then identifying that this f is a identifier, a variable in this case. Then there's a token that represents the equals, and another token which is also an identifier which stands for a function called here. Then there are these syntactic elements like a left parenthesis, which is a token, the minus sign, which is a token, the number 1, which is a token, close parenthesis, which is a token, and then the semicolon, which ends the statement. So at the end of this process, we get this stream of tokens coming out of the lexical analysis part. Even in this very simple example, we can see that there are two types of tokens. There are some tokens that have attributes. For example, if I have an identifier, I need to know what the identifier is, otherwise I can't do anything useful with it. In the same way, if I identify an integer constant, I need to know the value of that integer constant because of course it matters for the computation I'll do with it later. Identifier name is called the token, or the token name, and the value that you get from matching it for a particular program. So in this particular case, we've identified sqrt as a sequence of characters that's a lexeme for the token called t_ident, which stands for an identifier. Other tokens do not. Like the token for while, it doesn't really matter what the lexeme is because we know it'll just be the letters WHILE, right? We also need to store the source code location for the error reports. That's part of the job of the lexical analyzer. And further, the specification of this token is something we'll call a pattern. So a token is defined using a pattern. For example, a pattern for an identifier could be just something you write down in English as a specification, which is a sequence of one or more letters, digits, and underscores, which starts with a letter or underscore. It's a way of describing what identifiers should look like in this particular programming language. A lexical analyzer has two jobs in the compiler pipeline. The first job is to identify the start and end character. So if you are trying to figure out where an identifier is in the input, it needs to know where the start character of that identifier is and where is the end character of the identifier, so it can return the lexeme for further processing. So that later on, when you want to call this function sqrt, it knows that that's a function to call because it knows the value of the lexeme. The other job of the lexical analyzer is to raise errors if there's any malformed input in the program. But as we'll see, it's not always so clear what a lexical error should be. Let's take the same example as before, except remove the spaces from it. Now, maybe the user did this accidentally, maybe on purpose. Let's say the user did it accidentally and removed the space. The counterintuitive part is that it doesn't result in a lexical error. And the reason is there is a valid token in this input. So if I look at this input sequence, I can see that there is a reserved word double in there. But if I add the f without a space, and this is a case where the white space is important, you can see that it matches the definition of an identifier. So in this particular statement, it's going to treat it as if it's a variable being assigned a value from a function call. In particular here, you don't get two tokens. You don't get the double reserved word for the type and followed by an identifier f. The removal of the white space between those two tokens means that you get a single token identifier called double F. It's important to note that the Lexer does not check for syntax errors. So even if you have a identifier in a context where an identifier doesn't make any sense, the lexical analyzer's job is not to catch these kinds of syntax errors. That's the job of the future step in the pipeline, which is parsing or syntax analysis. There are very few error types typically. There might be illegal characters where it's not a valid input character. Let's say you only accept UTF-8 as valid programs and it's UTF-16 or some other encoding. You can have unclosed string constants or comments that are not terminated correctly. So there's very few of these lexical error types. From those previous examples, it should be clear now that a lexical analyzer should not be disambiguating tokens. It should not look for the context and decide what this token should be or shouldn't be. It should just identify the tokens based on the patterns it was given. A good example of this is a unary operator, which the minus sign, which we can use for things like -2. So this minus here is a unary operator, but 2 minus 5 is a binary operator. In both cases, we have this minus sign here. From the context of the program, these are quite different because one is a unary operator, one is a binary operator. But for a lexical analyzer, it should not care about the context in which this operator is used. So it should just say this is the T minus token. So it always provides the same token for both. It's the job of the parser to disambiguate based on the context. So a question for you to work out to see if you're understanding the material is, using the same token definitions as before, provide the sequence of tokens for this input, which is double with open parenthesis -1 close parenthesis. So provide the list of tokens for that input. Okay, so let's look at a fairly commonly used way to implement lexical analysis, part of the compiler. This is often called ad hoc lexer. And an ad hoc lexer essentially is a big loop and switch scanner. So it scans character by character. It's a big nested switch case statement, which looks for each character one at a time. So let's say that it reads in DOU. In this case, there could be different contexts in which you could see this. So let's say you see DOU and then it follows. What follows is an equal. You know that DOU is some kind of variable. It's followed by BLE and then a space. Then you know that it's a reserved word that refers to the double type. Or you could have DOU BLEF and then an open bracket. And now in this case, you know that it's an identifier again, possibly for a function call. So notice that you have to go one character at a time and decide what the token should be. And sometimes this might involve backtracking. So there's a lot of getC, ungetC calls. If you think about getC giving you a character, ungetC puts a character back into the stream so that you can go and, you can go to a different path to identify the token. In order to do this efficiently, because there's backtracking involved, you need to implement buffering. If you're streaming from some kind of stream where you can't really just ungetC easily, you need to implement some kind of buffering. And a sentinel is just a way to say, I'm going to start recording a new token from this character position. If something goes wrong, I go back to this sentinel over here. A sentinel is there for not just one character pushbacks, but if you want to reset and start again to find a different token. This can happen sometimes when you're doing comments or strings, which can be quite long potentially in a program. This kind of way of implementing a lexical analyzer is quite error prone. because essentially you're writing everything from scratch. And if you want to modify the definition, it's quite problematic because now you need to figure out where in this mass of switch case statements is the correct place to add this new keyword or this new definition of the identifier, etc. What I would like you to do is, if you get the PDF version of these slides and then you click on this link over here, it'll take you to a GitHub repository for the source code of Clang, and I've highlighted that particular function in the Clang source code that reads C++ tokens. So I want you to take a look and see how easy it is to understand or how hard. And the mental exercise I would like you to do there is to see, well, if you wanted to modify it, if you wanted to change the definition of an identifier slightly, then where would you change this code? Can you actually figure out where in this code you would change things to improve the lexical analyzer? As a compiler writer, there are two properties that would like to see in implementation of a lexical analyzer that isn't captured by a loop and switch scanner. We want to know if the implementation actually captures the language specification. So if you look up the language specification, it should tell us what the tokens are and what they should look like. And the way that usually language specification tells us that is by describing them in some notation or in language, like using the English language to say, here's what an identifier looks like in this language. So we want to make sure that our implementation exactly captures that specification. And the second thing we would like from a lexical analyzer, and in fact every component of our compiler, we want to show correctness. We want to be able to prove that our implementation is correct and matches the language specification. So the key idea is to separate the definition of the tokens from the implementation. So if I can define the tokens by using the specification and automatically generate the implementation, then we can sort of go a long way in answering these two questions that I've posed above. In order to do this, though, we need to reason about patterns and how they can be used to define tokens, recognize the strings in the program as tokens. And we want to do this in a way that the definition of the token gives us the implementation of how to match the patterns and correctly identify the tokens in the input. Let's look at an alternative way to specify the patterns we need for a lexical analyzer. This time, instead of using a big loop and switch scanner, we're going to define these patterns using regular expressions. Before we go into regular expressions, I'm just going to recap a little bit of background on formal languages. And a formal language is just a mathematically precise way to talk about sets of strings. And as you can imagine, if you're dealing with programs, which are cases of strings that we are going to read, we need to have a precise way of talking about the set of all programs, which essentially would be a set of strings of valid programs. We start off with the basic elements with which we construct the strings. We call them symbols. Each symbol we assume is of length 1, and we will use this notation here, so little lowercase characters to refer to the symbols. Take these symbols and we construct a finite set of them called the alphabet, and the alphabet is this Greek symbol sigma is the convention that we use to talk about an alphabet. It's just all the symbols that you will use in constructing this set of strings. So in practice, sigma could be ASCII, sigma could be UTF-8, could be this. Any of these could be a valid set of symbols. For the sake of simplicity in the slides, we will be only using a small set like, AB or ABC. A string then is defined as a sequence of symbols sort of concatenated one after the other. And the length is equal to the number of symbols. So here's a example string, which is symbol A followed by symbol A symbol B followed by symbol A followed by symbol B. And a convenient notation is to use the exponent. So a to the power 2 just refers to 2 a's. And this is convenient, so I can talk about 100 a's by just writing that instead of the more tedious way of writing that out. We have a special case, and this is quite useful, as we'll see when we look at how we can interpret regular expressions, and that's an empty string. And an empty string is a zero length string, so it is something that will be useful later on. At this point it might seem mysterious. Why do we need a string that has zero length? But it turns out to be quite useful. And then we take the alphabet and we add this special symbol epsilon to it, and this original set, the union with this set containing the empty string, is what we will consider to be a usual definition of an alphabet over which we define a language. Now, a language is just, as I said, a set of strings. So if I have an alphabet sigma, then sigma 0 is all the strings of length 0. So as we saw, the epsilon is a special case of a string of length 0. So sigma 0 is just a set containing the epsilon, the empty string. Sigma 1, this is assuming that the alphabet looks like that, is a string, all the strings of length 1 is sigma 1. And all the strings of length 2 is sigma 2. And so on. So you can construct sigma 3, sigma 4, etc. Now you can take the union of all of these sigma to the power I. So you can take sigma 0, union sigma 1, sigma 2, sigma 3, and so on. And you have sigma n. Now you can have n of any length. So this n tends to infinity means you can have a string of any length in this set of all strings. So what we're doing here is defining this special set. It's a set sigma star, and sigma star contains all the strings of any length from this alphabet. This is a way of saying that's everything that you could ever get, right? So a formal language is defined as a set of strings. So sigma star is a set of strings, and it's a formal language. But you can also define, just like you defined a pattern in English, you can use a math notation to construct a set of strings. So this, in the usual notation, this colon implies a condition here. So an, bn, where n is greater than 0, would be the strings A, B, and then if I add another B, A, I have to add another B, right? So I have equal numbers of A's and B's, and all the B's follows the A. So it has this nice sort of nesting property here. As soon as I add another A, I have to add another B. So one question for you is to write down a formula for how many strings will be in the set sigma n if the alphabet sigma has m elements. That will help you sort of understand what's the nature of this set and how quickly it grows. A way to describe this, so let's take into account the sigma that's like the set of ASCII characters. If I look at that sigma and I look at what sigma star looks like for the ASCII characters, you can see that it includes every book ever written, right? Because you can take all of these ASCII symbols, put them in some order, and among this set of sigma star, somewhere is going to be Tolstoy's War and Peace, or Pride and Prejudice by Jane Austen, or any of these different books exist somewhere in sigma star. In fact, there's a great short story by a famous Argentinian author called Jorge Luis Borges, called The Library of Babel. And he imagines exactly sigma star as this massive library in which every book that ever could be written exists. And people sort of wander the hallways trying to figure out which book is worth reading. A regular language is just a special case of a formal language, and it is defined in the following way. We just define the set of regular languages recursively. And again, we start from the symbols and then we recursively build up the set of regular languages. And the reason we do this is because, as we'll see, there's regular expressions that we're going to use in our lexical analyzer. Each regular expression will correspond to exactly one of these regular languages. So the base case for this recursion is the empty set. So the empty set here stands for a null set of strings. So basically a regular language that is degenerate doesn't recognize anything. Right? So that's not very useful for us. The other base case is this one, which is a set containing exactly one string, and that string is one symbol from the set of your alphabet and includes the epsilon, the empty string. Once we have the base case, then we can recursively define what a regular language is by combining these regular languages that are from the base case together. So let's look at the three cases. There are three cases here, A, B, and C. And these are the different ways you can take two existing regular languages. So for example, you could take something from the base case and construct a new regular language. And then you can apply this definition recursively to build further sort of sets of strings. Okay, so the first thing you can do is concatenation. Concatenation just means you take a symbol A and then you take another symbol B and you put them next to each other. So the B following the A. So that gives me a new string, AB. So what this says is if I have a language L1, and let's say L1 is all the A's that you can have, right? A to the I greater than 0. And I have L2, which is B to the J, and J greater than 0. Then if I concatenate all the strings from L1 and L2, right, I would get L1.L2 is equal to, I take a string from L1, which is, let's say, a 1A, and I take a string from L2, let's say 2Bs, and I concatenate them together. Or I could take 2A's, concatenate to 1B. I can take 1A and 1B. I can take any combination. And so you can see that all I'm doing is making sure that this set of strings here is all the A's be from L1 and then all the B's that can be from L2. And I'm concatenating them together to get this new regular language, which is L1.L2, the concatenation of the two. Union is really simple. It's just taking two sets. So if I take, for example, L1 union L2 from these two sets, then it's just all the A's, right? All the A's that can happen, and then you can have all the B's. Now they are not concatenated together like we had in L1.L2. In the union, we are just taking all the sets of strings that are A's and all the sets of strings that are B's, and then taking the union of those two sets. Finally, the last recursive case is called Kleene closure, and it's often referred to just by this operator star. So instead of Kleene closure, we often refer to as the star operator. So L star is very similar. So if you remember, you take sigma 0, which was all of the strings of length 0, union sigma 1, union sigma 2, and so on. And this was called sigma star. L star is exactly the same, except we have L0, L1, L2, all the way to Ln. And just like here, n can be any n. So it can be any integer that you want, tending to infinity. So it's the same idea, except you're starting from a language instead of the alphabet. That's the only difference. So for example, if I had a language like L, a regular language, which I can define as A to the I, where I greater than 0. So as we saw before, actually let me make this I greater than equal to 0 so that it also includes the empty string. Now this contains A's of length 0, 1, 2, 3, 4. So you can see that L star is going to be equal to L in this case, right? So if you apply the star operator to this language here, you end up with L star. So that's not always the case. So there might be some regular languages like, for example, if I have a regular language like A, N, B, M, N and M are greater than or equal to 0, and that's my regular language, then L star is actually not equal to L. It's fairly bit complicated because now you can have a mix of A's and B's. It's not always going to be the case that the B's follows the A's. And finally, the last rule in constructing a regular language is that there are no other regular languages other than what you can construct by using these recursive rules and this set of base cases, the empty set and a set containing a single symbol as a string. So that's all you can use to define a regular language. Each regular language and build a larger set, which is a set where each element is a set of strings. So R1 here is a set of strings. So let's say R1 is A raised to N, N greater than or equal to 0. And then maybe R2 is another set, which is B to the N, N greater than or equal to 0. And for these examples, let's assume that sigma is equal to just A and B, right? Not like the large alphabet. So each element here is a set of strings. So the set of regular languages is a collection of these regular languages. And so you can also write down a regular language as in the math notation of a set where, let's say that Rn is defined as a set which has A's preceding B's, and you should at least have one A and one B, right, in this case, because it's greater than 0. So that's one way to define a set of strings, is sort of a concise way. Instead of writing down these ... dots, right, we write it down in this math notation that makes it precise what I mean by this set of strings. And so it happens that a sequence of letters following another sequence of letters is in fact a regular language because you can define it using the same operations that I just defined in the previous slide. Now it's very hard to deal with this kind of set notation of regular languages when we want to do some kind of programming, because you have to define this set and it's in this mathematical notation. It's much more convenient to use some kind of specialized syntax to describe a regular language. And when we take a formal language and describe it using this kind of specialized syntax, you can think of it as a special kind of programming language used to define this formal language. So if I want to define a regular language, I could write down a mathematical set notation, or I could write it down using this special syntax, and then when I do that, it's called a formal grammar. So a regular expression is an example of a formal grammar, and each regular expression corresponds to a regular language. So if I take this regular expression over here, the notation here says there is an open parenthesis, then there's a symbol from the alphabet, and then there's a bar, which is, or the pipe symbol, which is called OR, and then a symbol B, and then close parenthesis, and then star. Star stands for the same idea that we saw in the definition. It's 0 or more strings of that language. So each substring here represents some regular language, and then we're building them together recursively, just like we did in regular languages, to create a more complex regular expression. So if I say that I want the set of strings over the alphabet AB, which ends in ABB, I can write that down in math notation, but I can also write it down in this regular expression here, which if I read it aloud is A or B star followed by ABB, right? So you can have A or B, any number of A's or B's in any order, 0 or more of them, as long as the last three letters are going to be ABB. A regular expression is defined in this almost the same way as we define regular languages, which is not surprising because we want a one-to-one correspondence between the expressions, the regular expressions, and the regular languages. So every symbol in the alphabet is a regular expression. And so if I have an alphabet with two elements, A and B, then A and B by themselves are regular expressions. If R1 and R2 are regular expressions, so now we're recursively building more complex regular expressions, we combine them using concatenation, which is simply putting two regular expressions one after the other. So for example, AB is a regular expression because we took an A, which is a valid regular expression, and concatenated with a B. You can also have more complex ones like AA followed by BB. So that's also a regular expression. Another thing you can do is alternation, which is the OR. So it corresponds to union, right? If R1 or R2 means you can either have any string in R1 or any string in R2. So for example, if I have A or B here, what that means is I can either recognize an A or recognize a B. Again, I can have more complex ones like AA or BB. Now this implies that I can have two A's or two B's and nothing else. And finally, the most useful operator is the star operator or the Kleene closure. And what this means is when you put a star after a regular expression, you can have 0, 1, 2, and so on in infinitely many copies of that concatenated together. So for example, A star is equal to the empty string, a single A, two A's, three A's, four A's, and as many A's as you want. Similarly for B star, right? And you can also now combine these together. So if I do put a star after this example, I can get, if I want to know what AA or BB star is, it's the empty string, because you can always have 0 of them. And then you can have AA, you can have AA followed by AA, or you can have BB, or you can have BB followed by AA. You see the picture. You can sort of do any combination of these as many times as you like, and repeat them, except the building blocks that you have are AA and BB instead of just A, like we had in this previous example. And there are no other core operators that are defined, so you don't need any more operators to define the set of regular expressions. But in practice, and when we're writing lexical analyzers, it's often useful to take combinations of some basic operators. Like for example, if I don't really want the empty string, because often it's not that useful to match the empty string if I'm writing down a pattern, then I can write down A plus, and plus just means that I have to have at least one A, and then I can have 0 or more A's after that. So this AA star would correspond to almost exactly like this sequence, except the empty string is missing, right? Because I'll have at least one A right over here. So I can't have the empty string in this case. Now, there's a lot of these sort of syntactic sugar, as it were, which you can use in order to construct regular expressions. So Lex, for example, is the tool that we'll be using to construct a lexical analyzer, can actually handle quite a few things that can be defined based on the core operators, but would be tedious to define if you had to do it just using the core operators. So for example, if I wanted to match on the beginning of the line, it is convenient to say I'll use a caret to say it can only match at the beginning of a line. Similarly, a $sign is used to specify that it could be at the end of the line. And so you can see it has a special syntax. So if I wanted to use a caret or a dollar to actually match a caret, then I would have to escape it using a backslash. It has all of the core operators like R star, it has alternation, and it has parentheses, and it has concatenation, right? So those are the core. So these ones would be the core operators. But then all the others are syntactic sugar that can be used to make your regular expression more concise and easy to read. So for a good example is this, which is a square bracket containing characters. And so here's an example of that. So if I have a square bracket with the symbols ABC, then it stands for I can accept any symbol from this set. So it literally is mapped into a sequence of alternations. Like it's literally means A or B or C. It just saves you a little bit of typing. Instead of typing this, you can type this, right? So another sort of convenient thing is if you have everything that's not a symbol. So here, the confusing thing here is that this caret and this caret over here are two totally different things. And this caret means a not operator. So it says, find me this square bracket specifies a character class. So it's all of the characters that are not A. And so if I wanted to construct a regular expression for it, it would be if my alphabet had B, A, B, C in my alphabet, then it would be all the symbols that are not A, right? So B or C, for example. So these are things that you will be more familiar with as you do your Lex assignment. And there is a Lex practice that's on the course webpage. I highly recommend you start, as you're ready to understand about regular expressions, doing the Lex practice will help you understand regular expressions in a deeper way. So we saw some advantages of using regular expressions because now we can exactly specify a pattern using regular expression, and we don't have to actually implement the matching because that'll happen for us. Something that interprets regular expressions can do the matching for us. And we'll see those algorithms in subsequent lectures where we try to understand how Lex would work, right? How does it actually do the matching? But are there any limitations, potential limitations of using this approach of regular expressions? One limitation that people say is, well, it could be slower than writing your own from scratch with, that's the argument that you don't want to deal with regular expressions because potentially they could be slow. As we'll see, that's not really the case. If you're clever enough about how you implement the regular expressions and the constraints you put on them, they can be just as efficient as a difficult to read loop and switch scanner. However, there are some so-called limitations. The regular expressions can only be used if your language definition is sane, so that you are actually providing a language specification where the tokens are defined in some limited way. Like it's not every possible token that can be defined. So one example, it comes from Fortran, where it's very difficult to write a regular expression to capture this sort of craziness that you can do in Fortran. So here, the only difference between 1 and 2, these two statements in Fortran, is the fact that I've changed a comma to a dot. Now, in this case, Fortran allows you to have spaces inside your identifier definition. So is this second case, it sort of tries to treat this as an identifier, but it's super long distance because you only know that it's identifier once you reach this dot over here. If it was a comma, like in this case, then it would be a do loop in Fortran. So this is a case where you probably shouldn't be using regular expressions to capture this. But one could argue that the language specification should not allow you to do crazy stuff like this. Another example would be palindromes. So a palindrome is just a symbol that can be is a mirror image. So you can see that A, B, B, A, these are mirror images of each other. Now you could construct a programming language that says your identifiers, so identifiers must be palindromes. Now you could say that, but I don't think that's a reasonable thing to say when you specify a programming language. But if you do, then we know that you cannot write a regular expression for a palindrome because a palindrome is not a regular language. So not only does looking at a regular expression give you some benefits in terms of correctness properties, but it also might be useful in constraining what you should put in a programming language. So any potential future programming language, maybe you don't want to support things like identifiers being palindromes because that doesn't really make sense.